This is the prototype of my next generation electrophoretic light scattering instrument, and I'm currently running a sample. It's a high conductivity sample. The ionic strength is about 1.8 molar. That's way beyond any commercial instrument can reliably even attempt to make a measurement. My next generation system can readily make measurements at such high ionic strengths. I'm going to show some features of what it's able to do. So while this is running, I'll describe what's happening. So electrophoretic light scattering can be done using a laser Doppler method, which gives you a distribution of electrophoretic mobilities, or Zeta potentials if you do the conversion. Or you can use phase analysis light scattering, which I invented for my PhD. And you do one or the other. No instrument other than this one is capable of performing both at the same time, whereas this instrument does. That's one of its patented features. And it's able to do it at high electric field frequencies, higher than is otherwise required to obtain a proper distribution of electrophoretic mobilities. So this is applying a sinusoidal electric field. We see that here. We see the yellow is the voltage that's being applied, and the red is the current that's being measured through the sample. And this plot here is a plot of the voltage versus the current. And this information is used to detect any electrode polarization, which is also indicated in one of these bars up here. This is one of the major problems with trying to do high salt concentration measurements, and to the best of my knowledge, no instrument on the market makes any attempt to monitor the presence of polarization and compensate the data accordingly. Any commercial instrument that would attempt this would have extreme polarization because of the low electric field frequency that's used, and also because of the materials that the electrodes are fabricated from, typically palladium in modern instruments. As you can see, the voltage and the current are very well matched in terms of their phase, so there's little polarization occurring in this sample, even though it is at nearly 2 molar ionic strength. This shows the instantaneous phase of the signal measured across 1 second. So the image, this is updating every 1 or 2 seconds, but all the data are being collected. So while 1 second's worth of data being processed, the next second's weight is being transferred to the memory for processing. I can see that because of the slope on this, I know there's some convection, which is not surprising because of the heating, which is the other problem with trying to measure samples like this, is the extreme heating that occurs. But because of the way that I do the Fourier transform for the distribution method here, it's immune to that. So even though there is a significant linear contribution, it doesn't show up in this distribution. So we can see a distribution of mobilities here, and you can see here that it's slightly positive. So the center peak is slightly positive. Simultaneous to this, and so from exactly the same light scattering data at exactly the same time, the phase function is being calculated. Now, because I'm applying a sine wave, this should be a cosinusoidal response, which is exactly what I see. And you can also notice how quickly it settles down. So within about 10 seconds or so, it's already got a well-defined cosinusoidal phase function. That's basically it. So this instrument allows simultaneous measurement of the phase function, so using the Powell's method and the distribution method. So, and I won't show it here, but the calculated electrophoretic mobilities using both methods are very well. They're very close to each other. Again, at the kind of frequencies I'm measuring, which is at 64 Hertz, a commercial instrument cannot generate the distribution. So by getting both, but because I'm using two different ways of analyzing the data, if I get the same result, then I can have very high confidence in the quality of the measurement. I can see the presence of convection, so I know it's there. I can see the presence or absence of electrode polarization, or in more extreme cases, if there's electrolysis. And also down the bottom, it's not going to show very well here, but I can see the temperature of the sample is 25.5 Celsius. And I measure the temperature in the sample. Commercial instruments typically measure the temperature inside the cell block. They are not measuring inside the sample. And I've seen examples of measurements on commercial instruments where it's clear that there's significant heating and convection occurring, and that the temperature of the measurement is not what the instrument claims it to be. The temperature here is the temperature measured about 2 millimeters above the laser beam in the sample. So that's what the next generation system can do.